Okay, so welcome back. Now, before we do an example, let me illustrate what's going on here, okay? Now, this is an exaggerated zoom in of the linearization of a function. So here we have our function, f of x, this curved line, and we have our tangent line, which is our linearization, right, of the function at a, okay? So here's where the 2 points meet. So if I take a small distance from a, so dx, so here's a plus dx right here, and so this distance between them is dx, the change in x, okay, or delta x, sometimes, as we denote it sometimes. So, now, if we go a small distance from a, then what we're saying is this distance dx, and what we're going to do is measure, okay, so this point is a, f of a, right? This point over here is a plus dx, comma, f of a plus dx, right? So that represents this point on the line. Now this vertical distance here in green, okay, is dy, right? That's dy. The derivative, or the differential dy, equal to f prime of a dx, okay? Which, to this point. Now this point is the approximation of f of x, or excuse me, f of a plus dx, right? So that's the approximation, the linearization here, that point. Well, that distance to that approximation, the point on the linearization, the tangent line, is dy. Now the purple line from the actual function, so this vertical distance is actually delta y, okay? So we could take delta x, right, or dx, right? So we could take a small change in x, and instead of using the actual change, delta y, we can use the linear approximation, and that turns out to be equal to dx. And that's equal to, based on our previous conversation, f prime of a dx. Okay? And so this is the error, right, between the two. But again, because we're talking about really small differences, this distance, this error, is really small. And as we've seen in the last video, it's okay if we want to use this approximation. Okay? And so that's what we're going to do. So next time we'll do an example.